You would have attempted few problems by now already. First problem, work done by static friction on an object may be positive, must be negative, must be zero, none of these. Maybe positive, right? Do you all understand this fact? Do I have to explain? No? So work done by static friction may be positive. Alright, let's look at problem 2. Right. So we have this movable pulley, fixed pulley, and the arrangement connected to a mass lying on a fixed inclined plane, smooth, frictionless. The system is released from rest, and the mass in a certain time traverses a distance 1 meter. Now, when this travels 1 meter, what's the distance moved up by the pulley? Half a meter. You realize that? That means the distance moved up by the other mass is half a meter, right? Now, all that we need to do is, for the system comprising this mass and these strings put together, we'll deploy work energy theorem, right? In this case, mg sine theta into 1 meter is the work done by gravity. Mg cos theta is not doing any work, right? Because that's perpendicular to the inclined plane, that's perpendicular to 1 meter. So the work done by gravity here is like ma g sine theta into 1, where theta is 37 degrees, right? That's positive work. mg sine theta acts like this, right? As far as this mass is concerned, mbg acts downwards and it's moved up by half a meter. Work done by gravity here is going to be negative minus mbg into half. Right? That's the sum total of the work done by various forces acting on the system comprising the two pulleys, the string and the mass. Do you realize that? And from work energy perspective, this must be equal to change in kinetic energy of the system. Realize that in a given time, while this travels 1 meter, this moves up by half a meter. That means the ratio of their velocities, if the velocity of this is like v, then the velocity of this is 2v, isn't it? So at this instant of time, the whole system starts from rest with zero kinetic energy. So the final kinetic energy is like, this would have a velocity v and this would have a velocity 2v, right? Would be half of mb into v squared plus half of ma into 2v squared. Work done by various forces is the total change in kinetic energy of the system. That's the principle involved. As simple as that. Right? Can I look at problem 3 then? Can I wipe this off? How many of you got this right independently? Okay, very good. This is horizontal, not vertical. It's like this. That's the circle, right? Horizontal. So here we have an arrangement where there is a spring connected to a collar like this, and the mass of the collar is 2 kilograms, and there is a circular track that this is connected to. The natural length of the spring is given to be 7 meters. That means when the spring is in this state, it's elongated. Realize that then this is 12, this is 5, so this is 13 meters. That means the elongation in the spring in this state is like 6 meters, right? So x1 is 6 meters. Yes or no? And when the spring is here, it's relaxed. That means the elongation here is 0, right? Now, in its journey from B to A, the mass m is being acted upon by spring force, and the work done by the spring force is always negative of the change in elastic potential energy. So work done by the spring force is minus half k into x2 squared minus x1 squared. That's the work done by the spring force, right? What about the normal reaction? Well, look at this circular track. At any point of time, when the collar is here, let's say, when the collar is here, the collar, let's say, has a certain velocity here. Therefore, to negotiate this circular trajectory, it would be acted upon by a normal reaction. There would be a normal reaction acting at this interface, providing mv squared by r from instant to instant, right? After all, what other force could provide the normal reaction? But then it's a zero force because n is perpendicular to the velocity at this instant and is therefore perpendicular to the displacement from instant to instant. So n is acting only to provide the required centripetal force, but is not participating in producing work or energy, right? So this is the work done by the spring force. Work done by the normal reaction is 0. There are no other forces acting on it. There are no other forces acting on it, right? And this, from work energy perspective, must be equal to the change in kinetic energy of the system. That means half m final kinetic. Let's say when it arrives here, it has a velocity v. The collar has a velocity v when it arrives at A. So that must be half m v squared minus 0 square. This would enable computation of V. In fact, you don't even have to compute V. All that is required is you might just want to compute mv squared. Mv squared would be like a 36k, as you can see. Mv squared is 36k, right? That is 7,200. And we're seeking normal reaction at A. We're seeking normal reaction at A. Normal reaction at A would provide for mv squared by R. N would provide for mv squared by R. mv squared you have already computed is 36k by R, which is 5 meters, and so on and so forth. These many newtons is going to be the required normal reaction at 1440. C, 1440 is what it turns out to be, right? K is 200, so 40 into 36, 1440. Let's look at 4. Clear? How many of you got this right? Oh, okay, fine, very good. So then I'm sure you realize there was nothing difficult about it. It was straight out of the set of things that we've learned, direct application of work energy theorem, right? Oh, okay. So initially the whole unit is at rest, and the spring is in its natural state, no elongation in the spring, right? And the mass is being acted upon by a horizontal force, constant horizontal force F rightwards. Under the influence of this force, then the mass moves rightwards and the spring elongates, right? When the spring begins to elongate, it's going to resist that elongation. A leftward spring force would act on the mass M, right? So then, even though the mass would have a net rightward force F minus the spring force, there would be an acceleration, but the acceleration would decrease with time. Why? Because there would be greater and greater spring force opposing the mass M as the spring elongates further and further, right? So there is going to be an elongation produced. There is going to be an acceleration associated with mass, so the velocity would increase, but the acceleration would decrease. Realize that? So the velocity would increase at a smaller and smaller rate, isn't it? Now, after a while, the following would happen. At some point, the spring force would be exactly countered by the external force F, right? The spring force Fs acting leftwards for a certain value of the elongation, call it x naught. The spring force would exactly counter the externally applied force F, right? So the acceleration at this point would become 0. Agreed. But the velocity will not be 0, because by the time It arrives here, it has been constantly accelerated, so it would have developed a certain velocity v naught. This would be a position of equilibrium, but not a position of rest. It develops a velocity, it's not going to come to rest at this position. Its acceleration at this instant would become 0, but its velocity would be non-zero. So then, despite the spring force being exactly equal to F at this point, and this position I would refer to as a mean position, because net of all forces is 0, that position is referred to as a mean position. If the net of all forces is 0 at a certain position, that's referred to as a mean position. Now, from this point onwards, after all, it has the mass m would have developed a velocity v naught to the right. Beyond this point, so under the influence of inertia, the mass still moves rightwards. When it moves rightwards, the spring elongates further and the spring force increases. It becomes higher than the externally applied force. It's in excess of F, right? So then from this point, the mass does move to the right, but it begins to retard. Why? Because the leftward force becomes more than the rightward force F. Are you all there with me on this? No, Rosel? So the mass begins to retard. So its velocity will get killed. From this point onwards, its velocity will begin to get killed. So eventually you would expect at some point the velocity of the mass to become 0, because beyond the mean position, it's getting retarded. Right? So the velocity becomes 0. And when the velocity becomes 0, the mass can move no further. Right? And therefore, this becomes the extreme rightmost position of the mass, and this becomes the extreme rightmost position of the mass n. That means, under the influence of this force F, the maximum the mass could get displaced is this, and this amount of displacement would be commensurate with the maximum amount of work that the force F could produce. A constant force F, the maximum amount of work that it could produce would be commensurate with the maximum displacement that can take place in the mass n, point of application of the force. So one thing, up to this instant, whatever be the work done by the force F is going to be the maximum permissible work of this force. Beyond this point, what's going to happen? The velocity becomes 0, the spring force is larger than the externally applied force, the mass then begins to move leftwards. It doesn't have inertia enough to take it further to the right. The spring force becomes predominant and now taking the mass into its fray in the leftward direction. Alright, now let's say from the natural state to this state, L is the maximum displacement. So what would be the work done by the mass, by the force F? F into L. So then the only task ahead of us to be able to compute L. Now between these two states, let me call this state A and let me call this state B. Between these two states, who stops us from applying work energy theorem? Right? So between these two states, work done by the spring force is going to be negative of the change in elastic potential energy. So minus half K L squared minus 0 squared is the work done by the spring force, right? Work done by F is F into L. Work done by F is F into L. The initial kinetic energy, it starts from rest, and at this point it again comes to rest. So change in kinetic energy is 0. So yes or no? So that gives F into L is half KL square, or F is half KL. L therefore is 2F by K. L therefore is 2F by K. So the work done by F is going to be F into L, which is F into 2F by K. 2F squared by K. That's the maximum work done by the externally applied force F. I reckon the mistake some people could make as beginners would be that they would just assume that this becomes the point where the velocity becomes zero, and they would assume that this is the maximum displacement, failing to identify the fact that by this time it would have reached a velocity v naught, which would force it further ahead, and a further displacement under the influence of F could take place, right? That's the only conceptual error that one might make in solving this problem. Otherwise, it's a fairly simple thing to see. How many of you got this right? Okay, good. Let's look at 5. Hey, one thing, even though I may not have explicitly spoken about this, but power is rate at which work is done. Alright, so if a certain amount of work is done in a certain time, then the average power in that time is going to be the total work done divided by time. Otherwise, the instantaneous power is going to be rate at dw dt, rate at which work is done. Or the other way, if a force F acts at an instant when the velocity, let's say F acts at an instant when the velocity is v, then the power of this force is going to be F dot v. It's going to be F dot v. That's a power. The unit is watts. A bigger unit is ghoda, horsepower, right? 746 watts would comprise 1 horsepower, right? I was doing some engineering consultancy for a group somewhere, where it was an Indian group where most of the other people working were Sardarjis, and and the foreman of that place, and so suddenly, it was a mechanical unit, and then suddenly they said, कि साहब यहाँ का घोड़ा कमजोर है. I said, घोड़ा कमजोर है, ग्रुप फैक्ट्री चला रहा है कि घोड़ा चला रहा है, बग्गी कहाँ पर है तेरा, घोड़ा का है. And then it took me a little while to come to terms with it. That's where I learned this word ghoda from him. I said, oh, he's referring to the horsepower of the motor attached to that mechanical unit. So ghoda kamzor hai meant that it doesn't have enough horsepower in it to be able to drive that unit. So perhaps increase the rating of the motor means add more ghodas. That's what. Ghoda क्यों, फिर हाथी लगा लो. I mean, when they say the particle never stops, I hope you've read the problem. So we have a system, a surface where it's not a constant coefficient of friction, but a variable coefficient of friction. This is the origin. The coefficient of friction at a distance r from r equal to 0 is going to be a by r squared, where a is a constant. Now, the particle is initially at r equal to 1 and is imparted a certain velocity v naught to the right, Obviously, friction on it is going to act leftwards, but it will be a variable friction scenario. Why? Because mu itself is varying, right? So mu mg is going to be different at different positions of the block, right? So it's a variable friction scenario. So friction would act leftwards. Friction would act leftwards at any given instant of time. Friction, because the velocity would be rightwards. Now when they say that it never stops, what it really means is that, well, it goes all the way to infinity. Such is the velocity that you must impart. Well, if you don't impart it enough velocity, then friction would retard it so that it stops only at a finite distance. Then you want to impart it a certain velocity v naught so that it traverses all the way to eternity, right? So then, what we want to be doing is, at infinity, theoretical position means very, very far away from this position, right? The velocity just about becomes zero. This is like r tending to infinity. When r is very, very large, the velocity then becomes, or velocity comes closer and closer to zero. That's what it really means, right? Now, it starts here with this position, with this velocity, and goes all the way, very, very far away, and then it comes to rest. That's when you can claim that, well, it never stops. Mathematically, it never stops. If you look at an intermediate state, when it's at R0, the friction acting on it is A by R squared, leftwards, into mg, mu mg, that's a friction acting leftwards, right? Now, for a small displacement, dr to the right, what's the work done by the friction force? Minus F into dr, right? Because frictional force and displacements are oppositely directed. So the work done by friction to enable a small amount of displacement dr to the right would be minus F. This is F, so minus F into dr. That's the work done by the frictional force over a small displacement dr to the right. Now, between these two states, initial state and final state, the total work done by the frictional force, between A and infinity is going to be sum of all of this, where R starts from 1 and goes to infinity. So R starts from 1 and goes to infinity, right? That's the work done by the frictional force between A and B. Are you all on terms with this, right? And this is the only force that's doing work. Normal reaction is not doing work, mg is not doing work. So work done by this force must be negative of the change in must be equal to the change in kinetic energy. Final kinetic energy is 0 and initial kinetic energy is half m v naught square. So 0 minus half m v naught square. That's work energy theorem. Yes or no? So then obviously m gets cancelled. What we have is minus ag. 1 by r squared, when you integrate, you get like a minus 1 by r. So this becomes like a 1 by r, where r runs from 1 to infinity, right? And that must be equal to half v naught squared, right? And 1 by r, at r equal to infinity, 1 by r is 0, right? Minus half v naught square. And at r equal to 1, it becomes 1. So this becomes like a minus ag. 1 by infinity minus 1. So minus 1, that must be half v naught square. So v naught would be root 2 ag. Now what really happens is, if you impart this velocity, are you confused about anything? Anyone? If you impart this velocity at this point, it travels very, very far away, and then it would have lost all its velocity. Any velocity in excess of this velocity would carry it even further. So this is the smallest velocity that will take it to infinity. Higher velocities than this would cause it to have a non-zero velocity at infinity. That's what would happen. You know what I'm saying? 6. Ghoda? Anyone who's done Ghoda? हो गया, घोड़ा हो गया. Have you all attempted this? Now one thing, if you have a column of liquid in a uniform gravitational field, means G uniform, let's say this is a container containing a liquid. In a region where G is uniform. G is uniform means, well, this container is not of the order of the size of Jupiter, right? I mean, if it would be, let's say, comparable to the size of Jupiter, then you'll have variable G's available, right? But then this is much small compared to the radius of the Earth. I mean, it could be Eiffel Tower also. Then also we can imagine G to be practically constant. Not good enough to invoke variation of G over those heights and lengths, right? The radius of the Earth is like roughly 5,600 kilometers. So any dimension small compared to 5,600 kilometers would entail uniformity in G, much smaller compared to 5,600 kilometers. So then it's just a container, right? Now, besides the point, all that I want to tell you here is that if this is a uniform rho, even rho is constant, let's say, in this mass of fluid, that let's say same rho equal to constant, G equal to constant, this length is L, and let's say the area of cross section of this container is A. Area of cross section is A. Now if somebody wants to, and the total mass of the liquid is M, M. And now if somebody wants to compute the potential energy of this, provided rho is constant, G is uniform, then you can imagine this entire thing to be replaced by a point mass at the midpoint of this container. That means L by 2 units from here, right? So the potential energy of this is going to be mg into L by 2. You provided rho is constant, and provided G is uniform. And in a uniform container, this whole thing could be replaced by one single mass at its center of mass. Which is like L by 2 from the reference level. So the potential energy of this is going to be mg into L by 2. That's going to be the potential energy. Once you understand this fact, I will not be able to draw the ghoda. So let's try and solve the problem without drawing too much, right? So we have a container of water here, and the horse drinks water from a cubical container of side 1 meter. I can draw the container. Container of side 1 meter. The level of the stomach of the horse is like 2 meters. So let me just draw this stomach, which is like 2 meters. All right. I mean, you can always imagine the stomach to be point mass. But that's besides the point. And this is 1 meter. Assume that all the water drunk by the horse is at a level 2 meters from the ground. अभी जो पानी पिया यहाँ के सैडल कर गया 2 मीटर पे घोड़ा, ठीक है? Then minimum work done by the horse in drinking the entire water in the container is how much? Realize that water, whether it's in the container or it's in the stomach, is the same, right? We will assume, at least we'll assume that it's the same. Whatever be it, this entire mass of water can be replaced by the same mass m, 0.5 meters from the ground, 0.5 meters from the ground. If m is the mass of the water in this container, then for the sake of computation of potential energy of this mass of water, you can replace it by the same mass, a point mass, at a distance 0.5 meters from the ground, which is what I told you a little while ago, right? So that means, let's say this point mass m is getting elevated from 0.5 meters to 2 meters. That means it's getting elevated by an amount 1.5 meters. So there is gain in potential energy of water. There is gain in potential energy of water. Mg into 1.5 is the gain in potential energy of water. And that must be the work done by the horse, isn't it? Where did this energy come from? It came because the horse provided that energy. जो भी अपने मुंह से आवाज करके किया होगा, don't bother about that. But the horse provided this energy to the water. This must have been the work done by the horse so that this amount of water could get raised by an additional amount, 1.5 meters. So this is the change in potential energy of water. This must have been the work done by the horse. This must have been the work done by the horse. And to compute the mass m here, well, compute the volume of this into density. Volume of this is 1 by 1 by 1 into density 10 to the power 3 of water. So you know volume into density, so you know mass of this. G is 10 into 1.5. These many joules is the increase in potential energy, and that must have come out of the work done by the horse. Have you attempted 7? Hey, realize that whether it be this inclined plane or that inclined plane, the same change in potential energy, so therefore the same gain in kinetic energy. So on reaching the bottom, both masses have the same kinetic energy and therefore the same velocity because they have the same mass. So statement A is correct. Statement 2. Okay, one thing that you can see is that theta 1 is larger than theta 2. Right? Theta 1 is larger than theta 2. Statement 2. acceleration of A will be greater than acceleration of B when both are released to slide on the inclined plane. The acceleration in this case is going to be g sine theta 1 down the plane. The acceleration here is going to be g sine theta 2. Evidently, g sine theta 1 greater than g sine theta 2. So statement 2 is fine, right? Correct. Statement 3. Work done by external agent to move the block slowly from B to O is negative. Yeah, because when what really happens is B moves down under the influence of mg sine theta, right? Now when somebody says that he wants to make the block move very slowly from B to O, very slowly from B to O is referred to as a quasi-static movement, That means the mass B the mass B does move down, but it remains unaccelerated at all times. So then if left free, it will have an acceleration g sine theta 2 downwards, right? But then if there is a force restraining it, then that external force acts upwards, so that external force balances mg sine theta 2, so that the net acceleration is 0 and the mass moves really slowly, unaccelerated down the plane. You know what I'm saying? So then if this external force acts upwards so that it could be hauled from B to O very slowly, then the displacement is downwards, whereas the external force is acting upwards, so the work done by the external force ought to have been negative, right? So statement 3 is also correct. Now from the figure you can see that from this position A to this position B, there is a loss of elevation equal to 10 meters. There is a loss of elevation equal to 10 meters from A to B. See, one is 15 meters above the ground, the other one is 25 meters above the ground. So difference in elevation is going to be 10 meters. So there is, between A and B, there is loss of potential energy, and that must be equal to gain of kinetic energy. So loss of potential energy is like mg into 10, and that must be gain in kinetic energy, half m into v squared. Yes or no? So v squared then becomes like a 20g. V squared then becomes like a 20g, right? Now, let's say the radius of curvature at this point means this point could be equivalent to like an instantaneous circle of this kind. This point could be like an instantaneous circle of this kind, right? And this instantaneous circle, let's say, has radius r, So at this point B, it's negotiating a circular trajectory of radius r. What would be its centripetal force requirement? mv squared by r. Okay, now the force is acting on it. When it is here, there is normal reaction acting upwards on this, and there is mg acting downwards. Now the centripetal force requirement is met by the connivance of this mg and n. They come together to provide the necessary centripetal force. Mg minus n together would account for the required Centripetal force of this is met by the difference of mg and n, where n has to be greater than or equal to 0 if contact has to be maintained. N has to be greater than or equal to 0 to maintain contact. Right? That means if this is greater than or equal to 0, that means mv squared by r must be less than or equal to mg. Right? That means r must be greater than or equal to root v squared by g. R must be greater than or equal to root v squared by g. Right? Where v squared by g is 20. V squared by g is 20. Have I made a mistake? mv squared by r less than or equal to mg. R greater than or equal to, I'm sorry, v squared by, I'm so sorry, v squared by g. R greater than or equal to v squared by g. V squared by g is 20. That means r greater than or equal to 20. That means the minimum radius of curvature here must be 20 meters so that the roller coaster could be safe enough at this point. I mean, safety is lost if the forces acting are not good enough to provide for the required centripetal force to negotiate the required trajectory. The trajectory could get lost if not ample centripetal force is provided for, and then it will run out of track and will cause severe injuries. Right? So safety means that the minimum radius of curvature here, it must be modeled in a manner that the minimum radius here must be 20 meters. Anything in excess of 20 meters is good enough. Anything in short of 20 meters is going to be disastrous. It's not going to provide enough centripetal force to negotiate the required. Got me? So the minimum safe value of radius is 20 meters. A. You want to be able to attempt 9. Have you attempted 9? Okay, now from the concept that I just mentioned, attempt 9. Now you know what the potential energy in a certain volume would be like, right? You can replace that entire thing by a point mass at its geometrical center, right? Now use that concept and take a fresh look at 9. Okay, so here we have a hollow cube whose volume is a cubed, right? And then this dotted portion is filled with water, and has a volume v by 4, Now realize the dimensions are a by 2, so a squared by 2, and then say this length is x. So then volume would be A into A by 2 into X. That's going to be the volume of this. So this X is like V by 2A squared, right? Where V is A cube. So this is like a by 2. This X would be A by 2. Okay. Now this is A by 2. So this is also A by 2. Now the potential of this is as if the entire mass of water here is contained at the midpoint of this volume V by 4. That means A by 4 above this level, A by 4 above this, right? This is A by 2. So that means the midpoint of this would be like A by 4 above this level, right? So then that's going to be A by 2 plus A by 4. So above the ground, the height of the water column is like A by 2 plus A by 4, that is 3A by 4. That's the initial height of the water column, right? Now, eventually, this melts here, perhaps there is ice, it melts here and it occupies this region, So then, the volume V by 4, which is like A cube by 4, now spreading over an area A by A and over a length L, over a height L. So then L becomes like A by 4. So then the height above the ground for the melted portion is going to be H2, which is like A by 8 above the ground, which means now the fallen elevation is what? H1 minus H2, that's the fallen elevation. Which is like 5A by 8. That's a fallen elevation. The work done by gravity in the process would be fallen mg into fallen elevation. Mg into fallen elevation would be the work done by gravity. Where m you can compute from the volume into density. This is V by 4, that is A cube by 4 into density, right? M is going to be what? The volume is A cube by 4. This volume is A cube by 4 into density rho. That's going to be the mass m. That's going to be the mass m, volume into density rho, etc. So C 5 by 8 mga. Okay, we can just go ahead with mg into 5A by 8. We don't need, we know m, right? So how many of you got this right? Yes, did expect. Okay, I'm not discussing 10 right now. I have not discussed equilibrium with you, but just one thing that I want to tell you here is that there are two things. Equilibrium means force must be 0, and force is like minus du dx. If this becomes 0, then that's a position of equilibrium. When u is the least it could be, that would be a position of stable equilibrium. When u is the least it could be, then that's a position of stable equilibrium. Now in this case, at x equal to x1, du dx is what? Slope of the u versus x graph. That means slope of the tangent at any given x. In this case, at x equal to x1, do you realize that the tangent is inclined? At x equal to x1, look at the figure, at x equal to x1, the tangent is inclined. So du dx is not 0, so it can't be a position of equilibrium. What's given is u versus x. At x equal to x1, this is the slope of the tangent, which is not 0. So du dx is not 0 at x equal to x1. at x equal to x2 once again. This is the slope of the tangent. So du dx again is not 0 at x equal to x1 or x2. So x1 and x2 are not positions of equilibrium at all because f is not 0. Du dx is not 0. Right? So if they are not even equilibrium, okay, this is x3. So x3 is not a position of equilibrium. And x2. x2 is this position. x2 is this position. At x equal to x2, the tangent is parallel to the x-axis. So slope of this tangent is 0. So du dx is 0. So force is 0 at this point. But then u is high. The highest value of u will not give you stable equilibrium. So it's equilibrium alright, but not stable equilibrium. At x equal to x2, the force is 0, but it's not stable equilibrium. Stable equilibrium would be, let's say, for example, something like this. At this point, du dx is 0, so force is 0, and u is the least. So when u is the least, then that's a position of stable equilibrium. That's a position of stable equilibrium. So option A is scrapped. Option B, x2 is in equilibrium but not stable equilibrium because this is the highest maximum value of u. Maximum value of u will not lead to stable equilibrium. x3 is not even in equilibrium because du dx is not 0, so minus du dx is not 0, and so on and so forth. Okay. 11, problem 11, what's the answer? Alright, so in problem 11 we have a spring which is originally in its natural state. A mass m is attached to one end and the mass m very slowly moves to an equilibrium position. That means what's done is, this mass is held here at this point and this palm is slowly lowered. That means the spring does extend, but the mass never gathers velocity because the palm is preventing it from gathering velocity. Right? So eventually, when it goes down, the spring gets elongated, mg remains the same, the spring force upward increases, whereas mg remains the same. So there would be a position where mg just about becomes equal to the spring force, and that's going to be the equilibrium position of the mass m, right? This is the equilibrium position of the mass m. X equal to x naught. At this position, the spring force is going to be kx naught upwards and weight is going to be downwards. Equilibrium means mg must be equal to kx naught, right? So x naught is like a mg by k, right? Now S be the gain in spring energy. So gain in spring energy is what? Half k x naught squared. That's the gain in spring energy. So which is like a half k into mg whole squared by k squared. Yeah. Thank you. Mg whole squared by 2k. That's a gain in spring energy. That's the gain in spring energy. Half k x naught squared. Right? And G be the loss in gravitational potential energy. G is like a mg into x naught. So mg x naught is what? Mg by k. So evidently G is 2 times S. Evidently G is 2 times S. That's option C. G is 2 times S. Option C. Clear? We have a force field, problem 12. Force field F given by 4xy I cap plus 2x squared j cap. The potential energy associated with this force. Okay, realize that the x component of the force is like a 4xy. 4xy? Yes or no? And that's obtained by differentiating u with respect to x, keeping y constant. So this must be like a minus dou u dou x. Differentiate u with respect to x, keeping y constant. Keeping y constant. See, that can happen in option C alone. You see that? Option C? Option C. If you use option C, then fx will turn out to be this, and fy, which is like a minus dou u dou y. Dou u dou y. If you differentiate this with respect to y, keeping x constant, you will get like a 2x square, right? That's option B. Option B. Option B should be the right answer. See, because if you differentiate this with respect to x, keeping y constant, minus dou u dou x, option B is like u equal to minus 2x squared y plus a constant. So, minus dou u dou x would be like a 4xy, which would be the x component of the force, 4xy, right? And minus dou u dou y is going to be the y component of the force. Y component of the force, that's going to be minus 2x squared. 2x squared, that's all. 2x squared. So that matches with this. That matches with this. I told you this, right? Fx would be minus dou u dou x, Fy would be minus dou u dou y. Did I speak about it? Okay. Problem 13, pretty simple, because a particle with total energy E moves in a one-dimensional region where the potential energy is ux. The acceleration of the particle is 0 where the force is 0. So wherever the acceleration is 0, minus du dx must be 0. That means du dx must be 0 wherever the force is 0, and at that point the acceleration is going to be 0. So that makes option C eligible. C is correct. Uxy is cos of x plus y. So x component of the force is going to be minus dou u dou x. Right? That means if you differentiate with respect to x as if y is constant, you're going to get sine x plus y. And then x plus y with respect to x is going to be 1 as if y is constant, right, from chain rule. And the y component of the force is going to be minus dou u dou y, which is going to be sine x plus y. Right? So the required force vector is going to be Fx I cap plus Fy j cap. And we need the force at x equal to 0 and y equal to pi by 4. So in this, put x equal to 0 and y equal to pi by 4, you will get the x and the y components, Fx and Fy of the force at that point. You know what I'm saying? Have you attempted 15? No? Please stand by. A particle is projected with a velocity u, making an angle theta with the horizontal. The instantaneous power of the gravitational force at some instant of time t. At an instant of time t, it has a horizontal velocity which is like a u cos theta and has a vertical velocity which is like a u sin theta minus gt, right? So its velocity vector is like a u cos theta I cap plus u sin theta minus gt j cap. That is its velocity vector. The force vector is like a minus mg j cap. The gravitational force vector is minus mg j cap, right? The power of this force is going to be F dot V, right? So the power of the gravitational force is going to be F dot V. And this dot to this, realize that J dot I is going to be 0. So that's simply going to be minus mg into u sin theta minus gt. Realize that p versus time is a straight line. So it varies linearly with time. Power varies linearly with time. Varies linearly with time. Right? Look at 16. P versus T is a straight line. It varies linearly with time. Yeah, there is a voltage problem. You might want to switch it off for a while. There is also a sound problem. Alright. So well, this rope of length L and mass per unit length lambda, mass per unit length lambda lies heaped on the ground, right? And then one end of the rope is pulled up with a velocity v, constant velocity v. So after a while you would expect the entire rope to be vertical. You would expect the entire rope to be vertical. After how long? After time t equal to L by V, isn't it? In this time t, the entire rope would be vertical. Is it not? No. When it becomes completely vertical, the length L becomes completely vertical. It has two things in it. It has kinetic energy, which is half mv square. It has kinetic energy, which is half mv square, half of mass which is lambda L into V square, and it has potential energy which can be computed by imagining this entire uniform rope to be concentrated at the midpoint. That means the entire mass lambda L to be concentrated at a length L by 2 above the ground, right? You can imagine, replace this by one single point mass halfway between the bottom and the top, right? So mg, which is lambda L into g into L by 2. That's the energy added. That's the energy added to the system. In how much time? In this time, this is the total energy, kinetic plus potential, added to the system in time t equal to L by g, L by v. So then, this must have been the total work done by the force. The total energy added must have been the total work done by a force divided by the time taken, which is L by v. That must have been the average power. That must have been the average power. Total change in energy divided by the time taken. That must have been the average power in this period of time. Got me? These many watts. Let's look at 17. How many of you got this right? Okay. 1. Can I wipe this off? All right. Power versus x is a straight line. Power versus, the slope of the straight line, as you can see, is this angle is theta. Then tan theta is this length by this length. This length is 2 units by 10 units. So 1 by 5, right? So slope of the straight line is 1 by 5. So then, and the y-intercept is 2. The y-intercept is 2. So then, the power, that is y, is mx, which is 1 by 5x plus c. Mx plus c, right? Now, the particle is moving along the x-axis. The particle is moving along the x-axis, right? At any given instant of time, if v is the velocity in the x direction, the force acting on it would be m dv dt. Force acting on it would be m dv dt. The power associated would be force into velocity. That's going to be the power associated at any given instant of time, right? At any given instant of time t, the force m dv dt into v, that's going to be the power associated with this particle, right? But this could be written as m. Realize that dv dt is like v dv dx. All of you know this, right? Is v. So this I might want to write as mv squared dv dx. That's the power at, right, at any given x, and that must be equal to 1/5 x plus 2. M is given to be 10 by 7, whatever. So then what you could do is v squared dv, mv squared dv is like 0.2x plus 2 dx. mv squared dv is 0.2x plus 2, right? Integrate both sides. When x is 0, the velocity is 1 meter per second. When x is 10, the velocity, let's say, is v. The velocity, let's say, is v. Right? Are you confused about anything here? You can use, this would be m into, see, when you integrate v squared, v cube by 3. So m by 3 into v cube minus 1 is, this would be 0.2 into x square by 2. That means 100 plus 2 into x. X, that is 10, final minus initial. I hope you realize what happens when I plug in the limits, and then you can compute v. This is the required v which could be computed. Have I confused you? No? Have you attempted 21? Please read 21. Okay, in fact, for that matter, have you attempted 19? How many of you got 17 right? Okay. This is what you did? Similar. Huh? Uh-huh. Same thing, same thing. Yeah. Same thing. Uh, 18? Have you got past 18? There is a hose pipe and there is a jet coming out of this hose pipe with a velocity v, and you want this jet to rise to a height h. You want it to rise to a height h. So then that means the minimum v, so that it at least rises to a height h, must be root 2gh. If the velocity imparted is greater than root 2gh, it will rise to a height greater than h, right? But then for it to at least rise to a height h, the velocity v, that velocity of the jet must be root 2gh, right? These many meters per second. Okay. Now this has a certain diameter which is 2.5 meters, 2.5 centimeters, 0.025 meters, which means the volume flow rate through this is going to be what? Velocity into area of cross section is going to be the volume flow rate through this. Meters per second into square meters would give me meter cube per second, isn't it? This is meters per second into meter squared would give me cubic meters per second, that is volume flow rate. The volume of water is spurting out of it, right? So the volume flow rate in cubic meters per second is going to be the area of cross section, which is like a pi d squared by 4, area of cross section is pi d squared by 4 into the velocity root 2 gh. That's a volume flow rate. That's a volume flow rate, isn't it? The mass flow rate m dot means kilograms per second. This is cubic meters per second. This is cubic meters per second. To get volume flow rate, to get the mass flow rate, multiply the volume flow rate by density, right? No? Multiply volume cubic meters per second by density, you're going to get kilograms per second, isn't it? You'll get kilograms per second. So multiply volume flow rate by density, that means rho into pi d squared by 4 into root 2 gh. That's going to be the kilograms per second. The kinetic energy per second coming out of it, that's going to be the watts, isn't it? Kinetic energy per second. So kinetic energy per second is going to be half m dot into v squared. That's going to be the kinetic energy per second. This is kilograms per second into square of the velocity. This will give me kinetic energy per second coming out of this, right? So these many watts. This is kinetic energy per second, where m dot is this. These many watts would be required. This is the power required. Kinetic energy per second, joules per second. These many watts would be required. Are you okay with this? Shayan? Who's the 19. How many of you got this right? Oh, I was not about to do this problem also. I thought all of you would have got this right, so I was kind of avoiding to do this problem. But okay, how many of you didn't understand this? Understood it, right? Hello? A particle is projected upwards with a velocity of 16 meters per second. It rises to a maximum height h. Well, obviously it's going to get retarded because of two things. Because of gravity, and there is also air resistance which will retard its motion, right? Its velocity will become zero at some height. Right? And then it will begin to descend. Right? And when it begins to descend, it eventually arrives at this point with a velocity less than 16 meters per second, because air resistance would have hogged up some amount of energy, right? Air resistance would have eaten up some amount of energy. So the energy that it left with, it would come back with lesser energy because of air drag. So it comes back with a velocity which is like, how much? 8 meters per second. It is known that the work done by air resistance is same during upward and downward motion. Maximum height attained by the particle is. One thing, when it's moved up, when it's going up, then air resistance is going to act down. But when it's going down, air resistance is going to act In both cases, when it's going up and coming down, the displacement is the same. Upward displacement is the same as downward displacement, right? That means, in order that the work done by the air resistance be the same, the magnitude of the air drag must have been the same in both cases. You know what I'm saying? I'll repeat. So, when it's going up, the air drag is downwards F. And the work done by air resistance is going to be, when it's going up, the work done by air resistance is going to be minus F into X, minus F into H is going to be the total work done by air resistance going in order to go from the bottom point to the topmost point, right? Now when it's coming down, air resistance would act up, right? So then what's the work done by air resistance when it goes down? F is acting upwards, displacement H is downwards. So the work done by this is going to be minus F into H. So then in a round trip, minus FH plus minus FH, that's the total work done by the air resistance, right? What's the work done by gravity? 0. In a round trip, it's a conservative force field. So work done in a round trip by gravity, by the forces of gravity would always be 0. So going up and coming down, work done by gravity is 0. So this is the only force doing work in a round trip, net work, and this must be equal to change in kinetic energy. So this must be equal to half of m into v squared minus u squared, 8 squared minus 16 squared. Yes or no? Okay. Now, when it's only going up, right? When it's only going up, then the minus F into H is the work done by the air resistance. Work done by gravity is going to be minus mgh, right? And this must be change in kinetic energy. So 0 minus half m into 16 square. Yes or no? So the rest is pretty simple, because this m you can replace by this into this by this, and you can solve for h, the maximum height. From these two equations you can solve for h, the maximum height. You just need to eliminate m from these two equations, and you could transpose and then divide, so on and so forth. Right. Or what you could do is, this f into h you can write as this f into h could be replaced by this, and you can simply solve for h, isn't it? This f into h is like 1/4 of this, which can be plugged in here. M and m would get cancelled from both sides, and you can solve for h. Yeah. How many of you got this right? Oh, right. Good. Let's look at 21. One thing, in this case the spring is not relaxed. The mass m is in equilibrium under the influence of mg and spring force. That means the spring must have been elongated in this state, right? If the spring is elongated, this was the natural length of the spring. Then let's say from here to here, the extent of elongation was x naught. That means the spring force must have been kx naught upwards, mg downwards. It's an equilibrium in this state, this mass. So x naught can be obtained from this, mg by k. X naught is mg by k. Now, so I know x naught essentially, mg by k. I know x naught. Now, when this mass m hits this mass and together they move up, one thing that I can presume is when this mass hits this mass, the total mass m becomes 2m. And let's say after they get clubbed together, they have a common velocity vc. After they get clubbed together, just after the impact, they have a common velocity vc. The total linear momentum just after impact of the system is 2m into vc. They move together with a common velocity after they get stuck to each other, right? And that must be equal to the total initial momentum brought by m. Therefore, vc, the common velocity of the combined mass, is like a v by 2. Common velocity of the combined mass just after collision is going to be v by 2. I preserved momentum in the vertical direction. Now, you could get cynical when I apply this, and rightly, because you might be tempted, if you're thinking enough, you might be tempted to believe, hey, conservation of linear momentum in the vertical direction on the system of masses small m and small m is not legal. In this case, I can't preserve linear momentum in the vertical direction. Why would you want to actually think so? You would want to think so because the two are under the influence of a net external force, gravity, isn't it? Gravity, mg and mg acting on both masses, that's unbalanced. So, in the presence of a vertical unbalanced force, gravity, why would linear momentum be preserved in the vertical direction, right? You're right. It wouldn't be. This is an approximation. What I have assumed is that when they hit each other, the time of contact is so small of collision, the time of collision is so small that the linear impulse brought about by the impact, that is change in linear momentum brought about, the change in linear momentum brought about because of the impulse is negligible, and therefore if the impulse is negligible, delta t is very small, the linear impulse will be very small, so change in linear momentum would be negligible. The change in linear momentum is practically zero, means linear momentum is practically conserved. So then this is like practically conserved but not actually so. This is an approximate equation that I have written. This is not true realistically, this is an approximation. I have assumed that the time of impact delta t is so small that the impulse brought about because of the impact is negligible. Impulse is change in linear momentum. That means there is negligible amount of change in linear momentum, right? The impulse of gravity is going to be mg into delta t. If delta t is very small, then mg into delta t would be very small. The change in linear momentum because of mg acting for delta t could be ignored for all practical considerations. Linear momentum could therefore be almost conserved in a colliding scenario of this kind in the vertical direction, right? So, good enough approximation if mg is not very large. If mg is very, very large, then mg into delta t cannot be ignored despite delta t being very small. But you know, here we are not talking of Jupiter colliding with Pluto, right? We are talking of, let's say, a few kilograms here and there. So then, few kilograms here and there with delta t being of the order of a few milliseconds, then mg into delta t is small enough to be ignored, right? So, we can preserve linear momentum in the vertical direction despite presence of an unbalanced gravitational force in the vertical direction, right? That's a good enough approximation. Okay. So then, the combined velocity just after collision, therefore, is v by 2 of now a lumped mass 2m. It's a lumped mass 2m now. One single mass 2m. With a velocity v by 2 now. That's a scenario. And the spring is not relaxed. The spring is elongated at this juncture by an amount mg by k, right? At this point, the spring already has a built-in elongation, right? Mg by k. Now, what is it that we are seeking? The value of v, so that the spring just about attains its natural length. That means the mass, we want this mass 2m to just about come to this point. We want the mass 2m to just about manage to arrive at the natural state of the spring, right? That means we want this to happen. We want the mass 2m to be able to arrive at this natural state with just about arriving means arriving with a velocity 0. V prime being 0. So between these two states, can I not apply work energy theorem, right? Now, from this point to this point, what's the work done by gravity? Minus mg into x naught. Minus mg into x naught is the work done by gravity. Instead of m, we have 2m, right? So minus 2mg into x naught. X naught is known to us, mg by k. So x naught is known to us, which is mg by k. Okay. What's the work done by the spring force? Negative of the change in elastic potential energy. So minus half k into 0 squared minus x naught squared. This is x equal to 0. And then from work energy considerations, this must be equal to change in kinetic energy. Final kinetic energy is 0 here. Initial kinetic energy is half of 2m into v by 2 whole square. X naught can be plugged in as mg by k, and then the rest could have been, we can solve for v from v. Limitation of time as a resource will prevent us from having more sessions on work, power, energy.